Good morning, everyone. So today I'm going to discuss some recent results obtained by my research group on the prediction of adsorption properties for a variety of systems in metal organic framework and covalent organic framework using Ensemble learning. So we are going to start by saying a few words about how we are going to obtain these thermodynamic properties of adsorption. So we are going to do that through the prediction of the partition function. And the partition function, as we know from statistical mechanics, is going to allow us to access any type of thermic properties of a system, whether it's a fluid or whether it's a nano-confined system like gas, for instance, adsorbed in metal organic framework and covalent organic framework. So we're going to start by looking at simulation methods that are going to allow us to determine numerically the value for the partition function under a wide range of conditions. And such methods are based on, let's say, flat histogram methods, and the Wang-Landau sampling is one of them. So I'm going to start my talk by saying how we've been able to work with expanded Wang-Landau simulations, how we've been able to design this expanded Wang-Landau method to determine the partition function in the grand canonical ensemble of a wide range of systems. Then in the second part, we are going to look at how we can use machine learning to accelerate the prediction of these partition functions. Doing so is going to allow us to interpolate or extrapolate beyond the range of conditions covered by the simulations. So in turn, this will lead us to a quick and efficient determination of the properties of adsorption. Of course, that's going to result in a considerable speed up of this process of probability determination. And finally, this is going to allow us to screen various candidates, various materials for application in gas storage and gas separation. So everything, in terms of the prediction of the partition function, is going to, let's say, rely on advanced sampling methods like the Wang-Landau sampling method that for which I'm showing some schematic of the method on this slide. So in essence, what's going to happen there is that we are going to use an algorithm that's going to extensively sample all possible configurations of the system. We are going to determine the Boltzmann weight, if you will, associated with each of these configurations, and that's going to allow us to, gain access to this density of state. So that's one of the algorithms that's available to do that. Other algorithms that I've listed on this slide include, for instance, transition matrix methods and histogram rewriting. So again, getting an idea of the density of state is what was the original method of Wang-Landau sampling was about. And what we've done in a recent year was to extend that to determine partition functions in a variety of ensembles. And today I'm going to specifically focus on the grand canonical ensemble because we are again aiming at determining the properties of adsorbed gases in metal organic framework, covalent organic framework. So what we're going to do in this case, and that's going to be the expanded part of the name of the method, we are going to use an expanded ensemble formalism. So essentially what we see here is that particles that we are going to adsorb in the system are going to gradually shrink or grow, and this is going to allow us to sample and determine with accuracy what happens when the system becomes very, very dense, whether it's a dense liquid, whether it's a dense adsorbed phase. And we've seen that it's extremely important for the accuracy of the partition functions that we determine. So this method overall is going to result in this expanded Wang-Landau approach. And to give you a quick idea, the kind of acceptance rule that we are going to deal with are shown on the left-hand side of the slide. And what we see appear in these metropolis rules, acceptance criteria, if you will, that's the ratio of the partition function for the old configuration and the new configuration. So doing so, that's how we can sample for any kind of value that we have for the chemical potential mu. So for any kind of number of particles in the system, we can determine the value of the partition function. So the canonical partition function Q of NVT for all possible numbers of particles, and hence the grand canonical partition function that's just going to be the sum of the QNVT weighted by exponential of beta mu n. So that's how we get to the partition function. And we see some results that we've obtained here on a simple system and in Argon. It's just as a test case, as a benchmark for the method. And that's what we obtained for the logarithm on the right, the logarithm of the partition function as a function of the number of atoms, argon atoms in the system. So again, to benchmark this, I mean, we've compared with other existing methods and experimental data. And for instance, here, there is a whole set of results of what we obtain at the coexistence, the liquid vapor coexistence for argon using the expanding one-Landau approach, comparing the accuracy of the results with the transition matrix method and the experimental data on argon. Of course, I mean, once you have the partition function, as I was saying at the beginning, I mean, you can actually access all types of properties, and that includes the free energy, that includes the entropy. And well, here are a few, let's say, results. I mean, the table for the Gibbs free energy along the vapor-liquid coexistence, and on the right-hand side, the entropy of the two phases at coexistence. And we have here the comparison of the experimental data shown as squares here with respect to the expanded one-Landau results for argon shown here as a line. So we see that there is a nice fit or a nice agreement between the two sets of methods. Okay, so of course, I mean, once now we have a reliable way of predicting the grand canonical partition function for a liquid, for a gas, for a liquid vapor type of system. Now we can start thinking about predicting adsorption properties of, for instance, carbon dioxide confined in a metal organic framework, in that case, an isoreticular metal organic framework, well, number one in that case. So what we do there is essentially, I mean, we do exactly the same kind of approach. So we have the unit cell, for instance, at the bottom on the left-hand side, and we do insert the well, the particles of, the molecules of CO2 to obtain, for instance, at some point during the adsorption process, the configuration shown on the right-hand side. So when we do that, obviously, we are going to be able to predict the the partition function, and from the partition function we can access any kind of property for the adsorbed fluid, which includes, for instance, the adsorption isotherm on the right-hand side for a series of temperature, and for instance, the excess Gibbs free energy, excess enthalpy, and excess entropy on the right-hand side. So again, for the adsorption of carbon dioxide, for applications as carbon capture and carbon sequestration in a metal organic framework. So now let's go to the second part of the talk, which is the combined use of machine learning and simulation methods to speed up the prediction of adsorption properties. So in that case, I mean, we've, in terms of machine learning models, in the machine learning methods, we've resorted to the use of artificial neural networks, so some kind of deep learning method. And in that case, what we've used is basically, I mean, knowing, training the model, if you will, on a few expanded one-Landau simulations, we've been able to predict the value of the partition function over a wide range of conditions. So for instance, here, the number of particles n, volume v, and temperature T. So the output neurons, if you will, are going to be, for instance, here, the partition function and the energy of the system. So we've trained that, and going back to the usual benchmark, that's going to be argon. So we've trained the model, the machine learning model, on the basis of a few, let's say, series of expanded one-Landau simulations. And of course, I mean, in terms of validation, then we can take this model and predict for other properties than those covered by the expanded one-Landau simulation. So that's what we have here at the bottom. And we've tested that across various properties. So, using equation of states. So that would be the Helmholtz free energy predicted with the machine learning model. Again, I mean, we can calculate any kind of property from the partition function, and that's what we have for argon on the left. We can even see how it's going to behave with respect to the coexistence, vapor-liquid coexistence for carbon dioxide, and that's what we have on the right-hand side. So again, a very good agreement when we test the model between the machine learning model and results obtained from expanded one-Landau simulations. So we have a nice method that's going to allow us, how to build a machine learning model to predict the properties of fluids for a wide range of conditions. So now the next step, obviously, is to think about what's going to happen, and keeping in mind that at the back of our mind, we want to be able to predict, well, everything that's going to happen for a gas separation, so everything that's going to happen for mixtures. And there, machine learning is going to become extremely efficient and extremely useful, in the sense that when we think about mixtures, that means that we have a multi-dimensional space to actually sample. And with simulations, with flat histogram simulation, that's going to be a tremendously computationally intensive task to perform. So there, I mean, machine learning is going to allow us to bridge, for instance, between the results obtained for a few sets of conditions. And we've seen, for instance, and that's what these two graphs on this slide are going to show, that we obtain extremely accurate results. So that's for a mixture of argon krypton, extremely accurate results at coexistence by using only a fifth of the data that we have from the simulation. So using just a fifth of the data obtained from the simulation is going to allow us to build a robust machine learning model that's going to be able to cover the entire range of farming conditions, for instance, in that case, for vapor-liquid equilibrium. So now, I mean, now that we have, let's say, tested a way to build a combined machine learning model on the basis of molecular simulation results, what we can do is apply that to adsorbed systems and to the prediction of adsorption isotherm, the Gibbs free energy of, let's say, desorption, which is going to be crucial to determine the cost of regenerating, for instance, an adsorbent. So we can essentially follow the schematic diagram that we have at the top here. So we start with some data sets generated by simulations. We train a neural network on the basis of this data set that allows us to predict the partition function of the adsorbed fluid, and in turn, the excess properties, for instance, here on the right, of adsorption of these fluids. Okay, so following the similar approach to what we had on, let's say, fluids in the previous slides for this presentation, what we are going to be able to do is to train and to predict the partition function using the machine learning that we've trained. So that's these are a couple of examples at the bottom, which is a very good agreement between the prediction from the machine learning model on the y-axis here, and on the x-axis that's plotted against the simulation results. So we have this nice, let's say, correspondence between the two sets of results, and in the case of the adsorption, in that case of a mixture of light hydrocarbons in covalent organic framework, we have this very accurate, extremely accurate prediction of the partition function for this two-dimensional or this binary mixture as a gas that's going to be absorbed in covalent organic frameworks. All right, so what we've done in that case, I mean, to improve the accuracy and the efficiency of the whole process, is to average predictions over several neural networks, several types of neural networks. So we've done, I mean, the usual type of, let's say, randomization of the data set, so that would be the k-fold cross-validation, removing any bias in the choice of specific areas of the data sets. So that's going to be the bagging. And we also varied the architecture of the neural network. So that's going to be the diversity ensemble learning method, for which I'm going to show some results a bit later on this slide. So essentially in that case, that means that instead of relying the prediction of a single let's say, of a single neural network, what we are going to do is that we are going to average the predictions obtained from different types of neural networks. And by different types, I mean simply, for instance, varying the number of neurons in the first hidden layer, number of neurons in the second hidden layer, and averaging, obviously, the predictions of these various numbers of artificial neural networks. So specifically here, the results that were obtained were based on averaging over roughly 8 neural networks with different characteristics, different numbers of neurons in the two hidden layers. So here is some results and comparison with some work that was done in other groups, for instance, on grand canonical and Monte Carlo simulations. So some work done in Bill Goddard's group on the adsorption of hydrogen on covalent organic framework. So that's the comparison between our ML model and the grand canonical Monte Carlo simulations. And on the right-hand side, that's the selectivity towards the adsorption of ethane and methane in the case when we compare the relative performance of COF 102 and COF 108. So essentially, I mean, here, as you can see, there's a much bigger ratio in terms of how much ethane is going to be adsorbed in covalent organic framework 102 with respect to methane than there is in COF 108. So these are a couple of applications and examples of what can be achieved by combining the machine learning model and training it on the basis of flat histogram simulations on the results of expanded Wang-Landau simulations for adsorbed gases in metal organic framework and covalent organic framework. So in conclusion for this talk, I've presented some ways of combining machine learning methods, artificial networks, mostly what I've talked about today, with flat histogram sampling simulations that are intensive, but are carrying out a thorough sampling of the contraction space. And these combined expanded Wang-Landau machine learning scheme are able to predict accurately and extremely rapidly, once the model has been trained, the predictions of adsorbed gases. So again, one of the crucial advantages of this combined approach is, of course, the fact that you can interpolate between results obtained from the simulation. You can also extrapolate beyond the range of conditions that are covered by the simulations. So again, I mean, this is done instantly. I mean, once you have the weights for the artificial neural network, so it's extremely quick. And well, most instantly, you have the results for the partition function and for any kind of thermodynamic properties without the need of carrying out additional flat histogram simulations. We've seen also how we can improve the accuracy via ensemble learning, so averaging the predictions of a set of artificial network with neural network with different architecture, different kind of properties. And we've seen examples on thermic properties of adsorption. So we've seen carbon dioxide, hydrogen, and we've seen mixtures of ethane and methane. And we've seen how we can rank the relative performance of two or more covalent organic frameworks with respect to gas storage performance and separation processes. So, all right, so now I'd like to thank you for your attention, and I'd like to thank the group who did the work, and obviously thank the funders for helping us carrying out this work. Thank you again.